Okay guys, so we continue designing controller by state feedback that I told you from the previous class. The main part of the course is we began to cover. Okay, so we saw that in the previous class we went to this point that x dot is equal to ax plus bu, and the y output is cx plus du. That's right. And we had the CISO system, single output, single input and single output system. So we saw that the state feedback designing controller that the rest of the semester we're going to talk about this. By the way, the next week I'm going to determine the date of the midterm. Okay, the state feedback. So state, this is a state variable feedback. That's right. So this is the gain matrix, as I told you that we have to determine gain matrix. Okay, and this is the control input, the same here. That's right. So now let me implement this u inside this equation. So x dot gonna be ax plus bu minus kx. That's right. Simply is ax minus bkx, and I'm writing as x vector because this is state variables, right? So easily this is a minus bkx. Bingo. So I'm writing here, by applying the input to the system, x dot is equal to a minus bk in x. Okay, I taught you when I was teaching you the general format of that. Remember, if x dot is equal to ax, if you remember, you have in the notes from my lectures that the solution of this gonna be, guess it, yes, EAT, matrix exponential at state vector at time 0. This is matrix, remember, matrix exponential. That's right. So now having that, simply you can just compare this with this. Your a is transformed to a minus bk. That's right. So the solution, general solution of the system, when you give the input to the system, gonna be what? E. Now this time a minus bk at initial conditions. Here we go. Understand? So because now you are controlling the system by what? By you. Understand? So, and obviously x at time 0 is initial state caused by external disturbances. What is that? You can be a disturbance, guy. You can be a disturbance. The simplest and trivial version of that is this. Look at here. If this is, remember, the vibration course, this is the vibration course. That's right. Mass spring and damper, undergraduate control course. If you stretch this from here by your hand, so this distance gonna be x at time 0, and when you release it, the dynamics begins. That's right. So your hand acted as disturbance to the system, as external disturbance to the system. So now we got the solution when you apply the state feedback to the system. Okay. Now let us see how it looks like in the block diagram, because we are in the control. So x dot is equal to ax again plus bu, when the u is what? U is kx, state feedback. Right? Clear, guys? So look at here, guys. bu, you are giving a u control command multiplied by b vector or matrix. Because for the MIMO system it becomes to a matrix. Okay, this is being summed, this sum plus plus, okay, being sum with what? Just look at here, guys, with ax. So we need a being sum with ax. So see, exactly I'm following the formula. This is a, okay, a, now x. So the result bu plus x gives you what? X dot. So the output of this is x dot. So this is x dot. But we need ax, so we need what? An integrator here, guys. Integrator. Here we go. This is integrator. Because integration of x dot dt is what? Is what? Is x. Obviously. Right? It is x. Huh? Why? For those of you, is dx over dt in dt. Integral of dx is x, obviously. So this out gives you what? This gives you x, right? X. So we made this, but your u, I said that, as you see here, we said that u is the state feedback, is minus kx. This is the controller that we designed. The name of the controller is state feedback. So what we're gonna do, so we got the x, so x comes here, multiplied by this x, multiplied by what? You tell me. Multiplied by minus k. This is minus k. So this gives you what? This gives you u. This gives you u. Here we go. Understand? So we made this. We are fine. Or made this. Understand? But we had also c is equal to cx plus du. For simplicity, I said that d is 0, assume. So we're gonna have y is equal to cx. We got x from here. So you have to multiply by what? You have to multiply by c vector. When it goes to MIMO, it's gonna be matrix. I'm gonna teach you actually. So this gives you what? This gives you cx. But if you say I don't need d, we need for simplicity d is not 0, okay? D is not 0, okay? You can make it complete. So du plus ck plus cx. Sorry, guys, cx. So cx. This is cx plus. So you need a plus here. Here we go. Plus. Plus what? Plus du. We have u from here. So it's enough. Let me change the color too. That I take a branch of u from here, multiply by what? By d. Here we go. And sum with this. And sum with this. Du plus cx gives you what? Gives you y. Output of the system. So this is simple block diagram of state feedback. Okay. After teaching you its mathematics, I'm going to go to MATLAB. Okay. So clear? Now we know how it works. So, but I have many things to do. First, a system where the reference input is always 0, or remember I talked to previous class, origin is called what? It's called a regulator system. A regulator system. Remember when I was in the previous class, I said we assume that we want to push our system, whatever it is, to the origin. So in the phase plane I taught you. If you start from here, initial condition because of disturbance, as I taught you, you want to go finally here to 0 and 0. Remember, if you start from here, you want to go here and here. So I'm gonna teach you the system that want to go to, as I said, in the room temperature, you want to fix it at 75 Fahrenheit. I'm gonna teach that, but for now I'm teaching the system that you want to push it to the origin. Okay, regulator system. Now I'm discussing regulator system control design. So we got that solution based on the state feedback is this: x at time 0. That's right. Now, guys, compare this with the simplest differential equation you have ever seen in your life. What is that? X dot is equal to ax. If you remember, I taught you the solution of this is differential equation, is e at at this. That's right. Remember? So now look at this very simple function. Guys, if a is greater than 0, any number, name it, what's gonna happen to this term, to exponential of at? This gonna goes to what? Infinity. So x gonna goes to infinity. So your system is unstable. Let me plot it. This is high school algebra, that's right, math. I'm gonna plot x over time. If a is I don't know, any number 2, it's gonna be like that. Goes. Does your system goes to origin? No, it's leaving the origin. It's leaving the origin. So your system is unstable. That's right. Now, if a, for this differential equation, I'm going to extend whatever I'm teaching to the state vector. If a is smaller than 0, what's going to happen to this again? This goes to 0. So x also goes to 0. Goes to 0. Origin. So your system is stable. So here we go. If I start from here, the system goes to here. Actually, because this is first order system, it can go here like this, because we have no damping. So this is first order differential equation. Or if you start from here, this one goes here. If you start from here, this goes here, like as first order systems. That's right, undergraduate control. So you know that the sign of this exponential a has effect on stability and instability of a given system. But now, here we go. We have state space LTI system. These are the vectors. So matrix exponential. This is single exponential. These are x matrices. K at x at time 0. What about this? Huh? What about this? So for doing that, instead of a, we're gonna say eigenvalues. I taught you eigenvalues of. This is very important, guys, because you're gonna find this k gain matrix based on the eigenvalues. Eigenvalues of a minus bk determines stability and instability of x. I'm gonna say what? Yes, it is. I have a mathematical proof for that. How? Here we go. So remember that x dot is ax plus bu by using state feedback. we got u is kx, so we got this a minus bk in x. Or on the other hand, x dot, after applying the state feedback controller, is a minus bk in x. What about that I go to undergraduate control and apply a Laplace to the both sides of this equation? It's going to be good. It's going to be s x of s, the first derivative, Laplace is this, minus x at time 0 for simplicity here, is a minus bk in x of s. That's right. I'm moving this to the other side and this to this side. So if I do that, you're gonna have s, but you cannot put 1 because you're dealing with the matrices. Here gonna be what? I, identity matrix, si minus a minus bk in x of s is equal to x at time 0. Right? Okay. So if I want to find this, finally, the solution. So you cannot divide because these are matrices. What you're going to do, you're going to multiply the both sides by what? You're going to multiply the both sides by inverse of this. So si minus a minus bk inverse. If you do that, simply you get x of s is si minus a minus bk inverse at x at 0. Okay. If you remember, I told you a million times, a given matrix inverse is adjunct of that matrix, adg, over determinant of that matrix. So determinant of that also follows this, right? So x of s gonna be adjunct of this, si minus a minus bk adjunct, or determinant of this. Now you know what is the name of this equation. Come on, I taught you. Yes, characteristic equation or eigenvalue problem. That's right. If I give you a matrix, its eigenvalue gonna be calculated as si minus a, remember, is 0. This is eigenvalue problem. I taught you in the vibration ME520. I taught you in the undergraduate control. I'm teaching in the robotic class. So this is eigenvalue problem, and I taught in this course. So now your matrix is a is a minus q. So eigenvalue of a minus bk is si minus a minus bk is 0. So the name of this is eigenvalue or characteristic equation. Remember, I told you. So this gives you eigenvalue of the problem. So this is the denominator. Denominator. That's right. Denominator in the undergraduate control gives you what? Poles of the system. Poles. Understand? These are the poles of the system. On the other hand, let me write like this. So your x of s, like a transfer function I'm writing, gonna be si minus a minus bk adjunct divided by, if you extend that like as I did several times, gonna be sa1 s plus a2 s plus an. That's right. Understand? At initial time. That's right. So if now a1 A2 and AN, which are the eigenvalues of this system. That's right, eigenvalues of this system, eigenvalue of the system are greater than 1/0. So when you decompose this, when you decompose back to the time, remember undergraduate control, x of t gonna be a in s plus a. Let me put this like that, s. Yeah. Remember undergraduate control a1. No, let me do another name. C1, C2, S plus A2 plus C3, S plus A3 plus Cn, remember in S, the fraction of this. Now if you want to find solution in time, you have to apply what? Laplace inverse. So x of t gonna be C1, Laplace inverse of this, remember what was that? Minus A1t plus C2 e minus A2t until Cn e minus Ant. This is n. I'm getting older, guys. This is n. Understand? So if A1, you see that finally A2, An, which are the eigenvalues of the system, are positive. So all of are positive. That's right. Wait, this is holding. Hold on. Oh, there is a sign mistake, guys. Let me fix it. Okay. We're gonna find this. That's right. This. So now this is gonna be A1. A1. Okay. We can Laplace inverse this. So if A's are positive, all of each of these gonna increase, and your system becomes unstable. So you get this. So your system is unstable. So if the eigenvalues, the take-home message is this, guys. If the eigenvalues are positive, your system is unstable. But if, let me change the color. If A1, A2, and the A and all are negative, your system is stable. Because this gonna goes to 0, this goes to 0, this goes to 0. So if eigenvalues is negative, your system is stable. On the other hand, guys, in the control, in the linear system theory, even for the nonlinear control, our intention is to place the poles or eigenvalues to be a negative of the system. Okay? Understand? Okay? Okay, so that's it. So that's why we have to, on the other hand, place the eigenvalues or the poles of the system. So poles of the system are roots of eigenvalue problem. Okay? Hold on. Now, after knowing this, let me teach you how to determine the gain matrix and implement it in what? In MATLAB. Okay, because at the end of the day, these mathematics are useful when you put in the MATLAB and then put on the real-time toolbox of MATLAB and then connect to the experiment. If you can't, these are trash. Okay, so what you have to know first is mathematics and analytical background. So now let's go to real control. Determination of matrix, gain matrix K using, this is the first method. We have three methods. Using transformation matrix T. This is different from transformation methods of robotics that I'm teaching. Okay. So for this LTI system, x dot is equal to ax plus bu, and u is the state feedback that we want now to determine this to finish our controller. So how k that forces eigenvalues of a minus bk to be desirable, mu1, mu2, and mu_n. Okay, and what we want, eigenvalues, I just taught you. We want that eigenvalues be its real part, of that, real part of eigenvalues must be negative. This is golden in control, golden formula. Okay, we want to design K that gives us negative real part of the eigenvalues. So, and we want a negative real part of eigenvalues. Okay. Okay, we want eigenvalues. Okay, or as I just showed to you here, see here, these are the poles, or on the other hands, negative poles of the system. Okay, so in the using the transformation matrix, we have many steps. Step one, you need to, as I taught you several times, check the controllability of system. Using controllability matrix B A B A n minus 1b. 2. Note that, as I taught today, for ODE, ordinary differential equation, see, as I did today, this equation, for ODE, we are solving for, remember, a S1t, E S2t, but means scalar exponential term. But in matrix form, as for the LTI system, we as I said to you right now, need to find eigenvalues, eigenvalues based on this formula, Si minus A. Remember, I just taught you that is going to be Sn plus A1 Sn minus 1 plus An minus 1 S plus An. We need to work with these coefficients, eigenvalues of based on this. So you have to determine, I'm going to give you an example now, A1, A2, An minus 1 and An. Okay, after doing that, 3, determine transformation matrix T as MW. What is M? M is controllability matrix B, A, B, An minus 1, B. What is W? W is this matrix. I have to look at a piece of paper because I never memorized it. Okay. What W is this? Is based on these coefficients: An minus 1, An minus 2, An 1. Now we are shifting to the An minus 2, this comes here, An minus 3, 1, 0. Now this comes here, as we have. So here you're gonna have A1, okay? So see, A1, oh my god, A1, 1, 0, 0, 1, last line 0, 0 and 0. This is W. You have to determine this, okay? A minus 2 and a minus 2, and after that step 4 to determine the gain or gain matrix is, you say S minus mu1 desirable eigenvalues or desirable poles. Okay, come on. Oh, it's freezing. This is what you want to have as desirable poles eigenvalues. S minus mu2 in S minus mu n. These are the given based on you. I'm going to teach you in the example. This gives you a alpha 1, not A1. This is going to give you, if you multiply a polynomial, plus alpha n minus 1 S plus alpha n. So you have to determine these coefficients. These coefficients, alpha n minus 1 and alpha n. So note that if the system is already in the form of controllable canonical Remember, I taught in the first class form. Then you don't need to calculate T matrix. T matrix is identity I. Okay, T matrix is I. Okay, and the 5 is the gain matrix is calculated based on, look at here guys, A1 is 1 AN, alpha 1 is alpha n. After doing this, it's going to be alpha n minus AN, alpha n minus 1 minus AN minus 1, alpha 2 minus A2, and finally alpha 1 minus A1 multiplied by transformation matrix inverse. This is general way to determine the gain matrix for feedback control design or LTI system. Okay, here we go. So I'm gonna just express the example to say what's happening. Example is this: if suppose that you have this LTI system, x dot is equal to ax plus bu, and this is third order system, so a is 3 by 3. You have 3 state variables, 0, 2, 0, and 0, 1, 0, minus 1, minus 3, minus 4. And your b, because this is CISO system, single input, single output, gonna be 0, 0, 1, single input. Okay, and what we want, you have a boss in the company, it says I have third order system like a solenoid actuated butterfly valve. After linearization, that gives you this LTI system. I want this desirable closed loop poles or eigenvalues of S1 or mu1 is -1 plus j, S2 is -1 minus j, S3 is -5. First of all, why your boss wants these desirable poles or eigenvalues of the system? You don't have to be blind, guys. You have to have vision. First, I taught you this in undergraduate control and vibration. You see that, as I said, we want to have a negative part to be what? To be negative. Real part must be negative. Real part of the poles are negative, 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 and negative. Because you want to make your system stable based on whatever I taught here. Look at here. Based on, here we go. Where we go. See? Look at here. You want that to be negative. That's right. Second, if you remember from undergraduate control, when you have a pair of complex conjugate poles, minus a plus bij or I, means that your system is what? Your system is under damped, like as the suspension system of your car, means your system gonna be like this. That's right. Remember, it was a very good response. Third is that you see that the real part of the third pole's eigenvalue is 5 times of real part of the others. Means that dominant pole are these, because at the end of the day, this is gonna appear in the solution of x like this, like say C3 over S plus 5. That's right. This is gonna appear like that. So if you put the Laplace inverse as I taught today, only this part of that, part 3. So x of part 3 gonna be e minus 5t C3. So if you increase time, this vanishes too fast with respect to real part of this. Why? Let me give you. This is general, okay, not specific, for teaching you. The solution of this system, third order system, gonna be, say, E minus t. This minus t comes from these minuses in vibration course and undergraduate control course. Sine omega dt, omega dt plus zeta over 1 minus zeta square cosine omega dt. These sine and cosine coming from this imaginary parts, remember? Plus c3 e minus 5/3. So these one come from here and here. These 5 come from here. That's right. So if you increase the time, to infinity, which of these vanishes fast? This vanishes fast, goes to 0, because -5 and -1. These are, you can do it in the calculator. So you want to have a dominant behavior of these poles. These poles. That's why intentionally your boss said this is -5. This is undergraduate control course. Remember? So now, but your system is LTI system. Okay? Your boss asked you design a U minus KX state feedback by determining K to give such desirable poles or eigenvalues of the system. I'm gonna solve the next week.